Hi, welcome to the fourth section of this course, Building Data Science Models. In our previous section, we learnt about doing statistics in Julia. Here is the first video of this section, Dimensionality Reduction. Dimensionality reduction is the set of algorithms used by statisticians and data scientists when data has a large number of dimensions. It helps make computations and model designing easy. We will use the Principal Component Analysis (PCA) algorithm for this video. To get started with this video, you have to have the multivariate stats Julia package installed and running. This can be done by entering this in the Julia REPL. When using it for the first time, it might show a long list of warnings. However, you can safely ignore them for the time being. They in no way affect the algorithms and techniques that we will use in this video. Let the package download. Now let's see how to do it. Firstly, let's simulate about 100 random observations as a training set for the PCA algorithm, which we will use. This can be done using the RANDN function. Now, to fit the PCA algorithm on the simulated dataset, we can use the fit function. This fits the PCA algorithm with a given dimension on the dataset with the custom parameters of the user. This can be done as shown. Here, the max out dim parameter is just the maximum dimension of the output dataset. Now, as we've created an instance of the PCA algorithm fitted on our dataset, we can explore its properties to understand the algorithm and its Julia implementation better. Firstly, to look at the dimension of the input dataset, which can also be called the observation space, we can use the inDim function as shown. Now, we already know the dimension of the input data, so we have to look at the dimension of the output data to check whether the algorithm has reduced the dimension of our dataset. This can be done using the outDim function, as you can see here. Similarly, the mean vector of the input data can be calculated by simply using the mean function on the PCA instance that we have already created. This can be done as you can see on screen. Now, to get the projection matrix that corresponds to the principal components returned by our PCA instance. In the case of multiple principal components, they are arranged in the descending order of their respective variance values. The projection function helps us get the projection matrix of the instance, as shown. To know the variances of the principal components, the principal vars function can be used. We will get a list of the variances of all the principal components of the output data, as shown. To know the total variance of the principal components of the instance, the tPrincipalVar method can be used. This will give us an idea of the amount of variance being captured by the selected principal components in the output data, as shown on screen. The RANDN function simulates a set of random numbers, which we will use later in the PCA exercise. Here, we generate about 100 random observations, which we will fit into the PCA algorithm for the dimensionality reduction task. The fit function helps fit the PCA algorithm to the input dataset, which we simulated in the preceding step. The desired dimension of the output data can also be included as a parameter to the fits function. This will help in deciding the number of principal variance vectors. The inDim function gives the dimension of the input data. It is the raw data to which we want to apply our dimensionality reduction algorithm. The outDim function gives the dimension of the output dataset. It is the dimension of the dataset after the PCA algorithm is fitted on the input dataset. That is, after the dimensionality reduction process is done. In the preceding example, the dimension of the output dataset is 1. Which can be verified by the outDim function as shown here. The mean of the input data is like the center of gravity of the data. It is the point or vector, depending on the dimension of the data, around which the entire dataset is spread. The projection is the scaled or reduced version of the input data. It contains the shape and dimensions of the output data as specified. The principal variances are the variance values of the principal components of the input data, or the variances of the dimensions of the output data, which is the projection which we saw in the preceding example. Sometimes we are interested in knowing the total variance being exhibited by the principal components of the dataset. This will help the analyst gauge the properties of the data and act accordingly. This will simply be the sum of the variances of the principal components. which we have seen in the previous step. Great! So this video got us introduced to dimensionality reduction.